if we need to, we can switch to the room. Okay, so the place where I wanted to start was with this simple idea of a gating mechanism and how that relates to a state space model. So I wanted to just take a look at this equation right here. And we're going to think of x sub t as an input. So we have like x1, x2, x3, all the way up to x sub capital L. And we're going to be like generating from that a output, which is the y sub t. But in the middle, we're going to have this hidden state, right? So presumably y is going to be a function of the hidden state here, which is h sub t. And this kind of simple gating mechanism is going to take the input x sub t and apply a trainable linear layer to it and some kind of an activation sigma. And that gives a g sub t. And then that becomes the sort of gating parameter, as we might call it, which takes what you might look as like a convex combination. So like it's a mixture of the x sub t, which is the sort of signal at that moment, and h sub t, which is the previous hidden state. So you can think of this mechanism, which is not the Mamba block or anything, but we're just kind of starting to zoom in here, as learning a mask of the x sub t. So it's going to take it's going to be looking at the input, this x sub t, applying a trainable linear layer that tells it how much of the input to mix into the next hidden state and how much of the previous hidden state. Right, so if it learned that, if everything was a scalar and it learned that g sub t is 1 for a particular x sub t, yes, x sub t is a current token. Yes, you can think of it as a word, or right now we're just kind of getting very abstract where it's like we have these tokens, x1 all the way up to xl, and at a given time state, we're going to evolve the hidden state by one time step. Okay. So if it learned, for instance, that for a particular x, g sub t was 1, it would be forgetting the entire previous hidden state and incorporating only the new token x sub t into the hidden state. And if, on the other hand, it learned that for a particular x sub t, g sub t was 0, it would be completely leaving aside the new token and just maintaining the old hidden state, right? Oh, sure, yeah, so it's still too small, huh? Right, so yeah, this is the idea of a forget gate in LSTM world. And so now, going back to this notion of the Mamba block, we kind of go back here. So what this is going to be is we're thinking of the hidden state in terms of a differential equation, and I think this is a typo here in the paper. This should be h prime of t, right, instead of h of t. So h prime t equals minus h of t plus x of t. So this is a particular instantiation of the sort of Mamba framework here. And so what that's saying is that this is called a leaky integrator. So if I look up leaky integrator on Wikipedia, we can think of this like a differential equation that is going to accumulate things from, this is still very small, isn't it? Accumulate state from a signal C, and then this minus A, so in this case, we were looking at A equaling 1, so it would be dx dt is equal to minus 1 times x plus C. So it's sort of like accumulating this C, but it's also leaking a little bit of it at any time. So that's how we should think of this kind of like Mamba block as in a very simple case, that it's going to be accumulating new signal from the x sub t, but at each moment it's also forgetting something, right? And in particular, as we saw in the previous example, it can forget based on what the new token is. So it could learn that certain tokens can be completely left aside, and certain tokens could even represent a time when you want to just flush the entire state, which was h sub t minus 1, and completely incorporate only the new information, which was the x sub t. So in this appendix C of the Mamba paper, they prove that for a particular instantiation of this Mamba block, it's just doing exactly the gating mechanism here, right? So this is kind of the simplest version of the Mamba block. It ends up being the gating mechanism, which we just discussed. Now, if we go back to what the actual algorithm underlying the Mamba block is, this is in section 3 of the paper, and it's, so let's look at this algorithm. Okay, so this is algorithm 2 in the paper. And let's just go through this quickly. And so we end up with, we have this input x, and it's got dimensions BLD. So B is like a batch dimension. L is this like capital L length of the sequence. And D is the dimension of the input space. So we can think of that like a word embedding. So if we've embedded the words into R subcapital D or R super capital D, and that's the dimension of this whole tensor, okay? And then A is going to be this parameter which evolves the state. We saw that before, so in the simple case we had, it was just the number -1 here. So we took A equals -1, that was that leaking coefficient, which sort of like caused the state to leak out slowly. But we can, so now we're going to try to generalize that idea of the gate to the notion where instead of just A being -1, A can be a linear transformation, and we're going to be evolving the time state, evolving the hidden state by this equation here. So H prime is equal to AH of t plus BX of t. So X is like this signal coming in. And then finally, the output is another linear layer times this H of t. Let me pause for any questions. I think I've kind of gone through a lot of things quickly, but this is like the basic schematic of the paper. So I'm going to pause and see if anybody has any questions. And if not, I'll just kind of keep going and we'll build this piece by piece because there's a lot here. And that's part of the reason why this presentation is a little bit disorganized, because it's easy to get tangled in quite a few papers that kind of all contribute to this picture. Waiting for people to type. Visual example, we'll get there, yes. The leaky gate helps the vanishing gradient or the other tricks to get around back prop. Yes, okay. So these are good questions, and we're going to get there. Okay, so the idea is that this model of the hidden state, and notice that the time is continuous here, leads to a discretization in various ways. So there's kind of this general form that you can evolve the hidden state by, and thereby get the output y sub t from the hidden state. And the idea here is that they've found a way to take this general framework of how to go from input x to hidden state h to output y, and do it in multiple ways. So in other words, you have this viewpoint in which it's a recurrent discretized system. This is the 2 in the middle here. And that is good for inference. Okay, so we can break it down into this kind of general framework of why is recurrent framework good for inference and convolutional framework is good for training. Okay, so let's see if we can get a demonstration here, a picture. Okay, so let's think about a convolutional layer here, and we're just going to talk about a one-dimensional convolutional thing here. So in that case, we have this kind of like signal, x1, x2, x3, and we have a filter of length, let's say lowercase k, and we convolve it with the last k tokens, and we get an output from that, and that's like our output. What's nice about this is that you can accumulate the gradients from a convolutional layer in parallel, right? So for each output token, you can look at the inputs, the effect that the convolutional filter has on that output token, and you can backpropagate through it. And in particular, you can do it in parallel. So you can do all of the backpropagation stages from this long sequence at the same time because they don't have data dependencies on each other, right? You can just look at them all at the same time. But the problem is when you do inference, you cannot do inference with a convolutional filter without each time running the entire filter again, right? So you have to do multiplications and summations that are the size of the filter in order to get the next token when you're doing inference. But with a recurrent formulation, you can do it with just a constant time computation, right? So you're kind of accumulating this state. You're kind of you're so in a way you're trading compute for memory, right? So like let's say that this h of t is your hidden state, and it's maybe a few hundred dimensions or something like that. So instead of running the entire convolutional filter again, you've kind of traded compute, and instead you're storing it in memory, and you can do a constant amount of compute in order to get the next hidden state and to get the next y sub t. So what they figured out is, did somebody have a question? I'm sorry. Somebody was speaking. Okay. So the kind of duality of the Mamba thing here is that you can view it both ways. So when you want to do training, parallelizable training, you can look at it from a convolutional point of view. And when you want to do simple constant time inference, you can look at it from a recurrent point of view. And that is that's the sort of innovation of the whole framework here. And it's kind of, like I was saying, there's kind of this thicket of about like 7 papers that have various dependencies on each other, and Mamba is sort of the culmination of them. And there's like various ones here, and we'll kind of go over what they all are. Okay. So we've talked a little bit about this duality between the recurrent framework during inference and the convolutional framework during training. Let me pause there for some questions, if anybody has them.
Sorry, thanks for the presentation. I think you mentioned earlier that for Mamba, there's this idea of a recurrence POV, where you're trading memory for compute, and I was wondering if you could give like some sort of analogy or simple explanation for why this is the case.
Oh,
Just trying to understand the intuition behind
that's the case. Yeah. So what the analogy I was making was so if you were to imagine a one-dimensional convolutional layer that looks at the previous, like let's say lowercase k tokens, and applies the convolutional filter to them, and then from those computes the next output. You can think of those previous k tokens that are being plugged into the convolutional layer as your context, right? And so the problem though with that is that I was saying it requires k arithmetic operations or asymptotically O of k operations at each step, right? As opposed to just like O of 1. But if you store this hidden state in memory, that's what I was saying, kind of trading it for memory, then you have to carry around more memory in the form of this hidden state, but you can just evolve it to one time step forward with a constant amount of compute. So that's sort of this trade-off between a recurrent framework and a convolutional framework. So the big picture is that the convolutional framework is a lot better for training, and the recurrent framework is a lot better for inference. And so the kind of genius of this paper is that you can have both. Okay, so that's sort of the zoomed out view of what's going on here. Okay, and the way that they've figured out how to have both is by kind of focusing on this simple framework. This is the continuous version of the framework, and optimizing for a number of stages along the way. So they've kind of allowed, by doing a lot of clever programming and a lot of clever mathematics, they've figured out how to let the model have its cake and eat it too, right? So largely parallelizable training, not 100%, and largely constant time inference here. And then the goal here is to allow us to accumulate a lot more context than we might have otherwise. So going back to the idea of a convolutional layer for a second, the problem there is that if I have this filter, right, and it's like length k long, and when I do this inference for each step, I convolve it with the last k inputs, and I get an output. So the context that I'm using there is pretty rigid. First of all, it can't expand and contract. It's always exactly k tokens long is my context. And also it's it, so in addition to being rigid, it requires this like update step each time. So I'm really doing a lot of work to kind of like go back and remember things that I already sort of learned. So that's the kind of goal of this H of T, is to allow a more dynamic and intelligent way to carry around this context. So I feel like let's talk a little bit about kernel fusion, right? So this is kind of one of the programming techniques that they have implemented here in order to allow the model to execute a lot better on a GPU. Okay, so the question from chat is, so in Mamba you can't increase the context. Oh no, so I was contrasting it with a very simple convolutional mode of inference where like the context is rigid, it's always exactly the size of the filter. But here, the idea is that because we're doing things in a more flexible way, you can allow the context, such as it is stored in this like H of T, to be a lot more flexible. And we'll talk a little bit more about that if we have time, where you can actually adapt the time step. You can be learning the size of this time step. And in fact, like this gated, returning to the intuition we had a second ago, the gated thing, that was a case where with this gate here, in effect, we took a time step, but we didn't pay for it, because all we did with this one was we said like, oh, okay, so suppose we have an X token that we don't care about and we just want to throw it away. Well, all we did was take a time step forward and say, no, I'm just going to preserve the previous H of T and ignore this token completely. So we can accumulate state arbitrarily long if we decide that we just want to ignore tokens time after time after time after time. So that's like a very simple illustration of how the context can be dynamic in its length, right? We couldn't do that before. Okay, yeah, so I was starting to talk about kernel fusion a little bit, and the sort of, for people who are not familiar with algorithmic fusion, the idea is you can take two algorithms that are maybe separately implemented and save memory and or compute by turning them into one algorithm. So a very simple example of that comes not from GPU world or machine learning world is like, find me if you say you're examining a combinatorial object, like you're saying, find me all subsets of this large set that have exactly 2 green elements or something like that, right? And so one algorithm is just generate all the subsets, and the other algorithm is take all of the subsets and filter out the ones that have like 2 green elements. Just kind of inventing an example at random. That takes up a lot of memory, because to return every single subset of a large set, that's a crazy exponential sized object. And then you have to pass it to the next algorithm, which sort of filters it out. But of course, no smart program or whatever do things that way. You would write like a for loop, which kind of just goes through the subsets one by one, not storing them all at the same time, and filters out ones that you want, right? So that's like the simplest example of algorithmic fusion. You take 2 dumb things, put them together, and it becomes a smarter thing. And so the big picture here is that they're going to do that with these algorithms that compute this like recurrence formula in order to do inference, but in a way that does not do what I just said in the context of the previous example, where it's like you don't go and compute everything first and then return it and then go through that and take it to the next stage. You fuse the 2 algorithms so that you never have to pass things back to more to larger but less efficient memory. That's this like H. So if we look at this like pyramid here, they've illustrated here, we've got the GPU SRAM. It's smaller and it's faster, and you've got the GPU high bandwidth memory, which is larger and slower. And the dumb way to do things is to have algorithm 1 compute a bunch of stuff using GPU SRAM, right? So we know that GPUs work in a sort of a block fashion. Pass everything back to the high bandwidth memory. That's like the return value of algorithm 1 or kernel 1. And then kernel 2 goes and gets it from high bandwidth memory and does the next stage of processing. The smart way to do things, if you can, is to keep everything in block format as long as you can. So combine kernel 1 and kernel 2 into a single kernel that never has to pass things back into the high bandwidth memory. It can keep them in block format in the SRAM for longer, and therefore achieve more efficiency. Okay, how much time do we have? We have 10:36 is the time right now. Okay, so I apologize that there's just a lot here, and I sort of feel like this presentation is too long, and I didn't have time to make it short, and I sort of feel like this presentation is too long, and I didn't have time to make it. So we're losing, I'm getting an echo here actually. Okay. Okay, so we talked about the analogy to the gate. We talked about the kind of broad strokes of this evolving formula here. Oh, somebody can mute, please, because I'm getting this echo. And we talked about the convolutional versus the recurrent formulation here. So let me pause time here. Okay, so here's a good question. I wonder why we're even using continuous time for sequences of discrete tokens. Right. So there's a couple of advantages to, let's call it like having a third lens on the problem, right? So obviously we can't literally use continuous inputs in the case where we're having these, tokens one after another arriving. That's an inherently discrete problem. But the idea is, by having this as the sort of rubric we can discretize the situation in various ways. So it's kind of like another knob that you can allow on the problem. So in particular, when you have like a differential equation like this, there are a lot of different ways to come up with a numerical solution that evolves one step at a time, right? So it's just like you start with these like initial conditions, you have what the derivative should be at each moment, and you kind of step forward based on what that derivative is. The simplest way is like forward Euler. Oh, sorry, so Lewis asked, can somebody explain what a gate is, gating in general? So the idea of a gate is that we're going to have, I'm going to scroll back down here to where this like example we had was. Right. So the gate here is, let's make it even simpler than this here. So suppose that at every time step, we took the average of the new token and our previous hidden state. We just took 1/2 times the new token plus 1/2 times the hidden state. That's a pretty rigid way of evolving the state, right? And it might allow for some kind of rudimentary learning of the parameters, but it's not that great. The idea of a gate here is that you can decide how much of the previous state and how much of the new token to incorporate based on the token that you're seeing. So you notice this g of t, which is the kind of like parameter that controls how much of the old state and how much of the new token to incorporate, is itself a trainable function of x of t. So you can imagine that, if it's transcribing words, it could learn, like this linear layer could learn that, oh, the word really has no semantic meaning, right? So it could learn to map that to a g sub t of 0, right? So it would, if it learned to map the word to 0 with this linear layer and the sigmoid here, then it would be in effect saying like, never pay attention to that word, right? So if let's say 0.5% of the words were it could then extend its context by that much just by virtue of learning that like trainable gate there. Okay, so the idea of this is that this kind of a perspective, this kind of a model, can allow for better performance on these tasks that involve copying, selective copying, and things like this. That the problem with previous iterations of this kind of like state space model is that transformers like drastically outperform them on tasks where it's like literally just remember what you saw, you know. So maybe like we'll give you some like sequences in a row, and the only thing we're going to train you on is like every time you see the combination like red, blue, green, you should know that the next thing is orange, and that's the only thing that you get points for, right? And you know, extended versions of that have been a pretty simply elucidated like limitation of previous state space models. So they've had trouble even remembering like very simple rules like that. And so by sort of isolating these tasks into these, so there's the selective copying task. There's another one called like the induction heads task. It's sort of brought into focus what were like some of the real stark limitations of previous state space models. Okay, and Mamba has really improved in that is the kind of headline. So there's a lot of potential reasons why, and the authors are very good about sort of elucidating those. But the headline is that like Mamba has overcome a lot of the limitations of the previous state space models, which are kind of highlighted by these tasks here. So the copying, the selective copying, and the other one is the induction heads task. Okay, let me pause there for a second for loud questions and sort of gather what we're going to do next here in our remaining 18 minutes.
I have a question. How do state space models compare to mixture of experts models?
Oh, that's a very good question. I don't think I know the answer to that. There is a thing called Mixture of Experts Mamba that is out now. And that might be worth looking into, MOE Mamba. So I would advise taking a look at that. I wish I had a better sense of how to draw that parallel.
Thank you. I'll look at that.
Chad looks like he has a thought on this. Yeah, there it is. Okay, yeah, so here's this induction heads task, and it's being, you can see that like the other previous state space models like just decay when the test sequence gets to a certain length, but Mamba stays strong. Okay, one moment, please. Let's get a couple of these other papers here, which if we do it wrong, we'll just make everything a big complicated mess, but if we do it right, we'll hopefully provide some of the context for how these things have evolved and why. Okay, so I'm gonna get hippo up here. There's the hungry hippo. There's how to train your hippo. That's fun. And so the kind of thread here is a lot of these papers are co-written by Albert Gu, and a lot of them are co-written by Tree Dao. So Tree Dao, the kind of thread there is that he has often figured out ways to do this kind of like the kernel fusion and the very hardware aware algorithms that have allowed this sophisticated processing. So let's see here. The other one, S5, right? There's That's fine. Okay. Got the train your hippo. Okay, so let's go into what the Mamba block actually is. Let's get a little more concrete in our last moments here. So here's an illustration. This picture here is a good thing to keep in mind in terms of what the Mamba block actually is and how. So this is this gated MLP thing that we talked about, where you take the old signal, you take the new signal, and you kind of like gate them according to this mechanism down here. And then you've got the Mamba block, and this is this H3, so that stands for Hungry Hungry Hippos. That was like one of the previous iterations of these state space models. And this kind of diagram here is supposed to illustrate how Mamba is sort of a combination of those two things. So obviously the gated MLP does not have any SSM subroutine at all. It's just this very simple thing, but it illustrates here how this like Mamba is an evolved version of H3 based on the gated MLP. Okay. So let me pause there for questions, and I might just wrap up because there's just a lot to say, but it's very dense. Can you say more about the role of delta? Yeah. Seems to govern how much sensitivity to the hidden state the model has at each turn. Exactly right. Mechanically, a large delta resets the state H and focuses on the current input. Yeah. So one thing I can do that is definitely, I would say, useful is point you to this discussion here by, where's this? It's not there. Okay. Conceptual question. So I don't know, this is just a great illustrative thing going on here. So it's on the issues board for the state spaces S4 repo. And it's a person that asks like 4 really good questions, and then Albert Gu just shows up and answers them. So I recommend reading this. It's very interesting. Okay, so here we go. Learning the time step. I'll send the link right now, and you guys can read it. So here's the link. Okay, so learning the time step. In the annotated S4, the step size is another parameter that is learned through the training. I'm not sure if you can do the same. Right, so these questions were asked after S4 came out, but just before How to Train Your Hippo came out. And just to give you a little context, How to Train Your Hippo is notable in that it sort of unifies a number of different models that were based on this sort of like broadly the state space model. So like they have the H3, which already existed, and it subsumes that into its model, but also these things called Legendre memory units, which were like previous versions of this. So the How to Train Your Hippo is pretty mathematical, this paper, and it provides the sort of like unifying framework for all of these state space models. But it is not until Mamba that they allow the system to be time variant, so that it can actually, well, I guess we'll get more into that in a second. Let me just address this question. Okay, so irregular sampling, the effect of deep layers. Okay, so learning the step size. And here's what Albert says. We do learn the step size. How to Train Your Hippo defines the interpretation of step size more formally. Your intuition is correct. Larger step size prioritizes recent history. Smaller step size waits further back. So there's this notion of a time scale that is inversely proportional to the step size. Okay, this is interesting too. So this is how he does it. I usually initialize the step size based on any intuitions about the data. For instance, short sequences could have longer deltas, and then train it. That is, let the model learn its desired context length. Okay, and notice this, what he says here. So this is a little bit, it was a little bit confusing for me the first time I read it. So if the data was discretized at 100 hertz, you may want the model to have a context length of 200, where if it's at 10,000 hertz, you might need a much longer context. So the word longer is a little bit confusing here, because you would think, wait, if you have a higher sampling rate, how are you going to also make the context longer in time? That's going to, you're going to have to remember doubly more things, right? But he means longer in terms of the number of slices. So that, like, if you have a high sampling rate, you may then 10,000 slices only represents a second, whereas before it might have represented 100 seconds. So the idea is you might need to turn up the number of slices that are included in your context if you have a high sampling rate, because that represents a shorter period of time for the same number of slices. Okay. So we were talking before about how the convolutional model could not learn anything about the context length. It just had this kind of rigid filter of length k, and it looks back at the previous k tokens, applies the convolutional layer, and moves on to the next step. But this is an example of having a more dynamic version of that. Okay, so this is very useful, I find. I'm going to pause for questions. Okay, I recommend people look at, I'm going to send you this link here. Mamba Minimal is a good GitHub to get used to the Mamba code. It's a very inefficient but easily parsed version of the Mamba model. So you can just read it. It's all in one file. It's very good. Let me pause once more for questions. So there's this whole kind of thicket of papers here. Some of them, this paper S5 is not by the folks here, but the innovation of S5 was to take the S4 model and apply a more efficient version of the scan. So scan is kind of like, I guess, a fancy algorithms word, but it's just like the general version of prefix sum. So if you can imagine why that's related to this recurrent model. So it's like, if you have a bunch of numbers, let's say like 1, 7, 9, 2, then a prefix sum takes the running sum of all this. So 1, 7, 9, 2 becomes 1, 8, 17, 19, right? So it's like the running sum of all the things you've seen so far. And you can generalize that to more than just addition. So if the sort of associative operation is like evolved to the next time step, then you can imagine why a very efficient implementation of such a thing would be super useful to do inference on a long context where you have this kind of like recurrent model for inference. So that was the innovation of this paper, the S5 paper. So the Hippo paper, we haven't talked about. So another very good resource, if you haven't already seen it, is the annotated annotated S4. And this goes into, I think, about the right amount of the mathematics. And I think you can kind of skip what you're not interested in. It talks about how we're expanding things in these polynomial bases here. Looks like we have about 6 minutes left, so I will. Dumb question, but do A, B, C get calculated by input X only? So let's go back here to the Mamba paper, and let's look at algorithm 2. Yes, so A, B, and C get calculated from input X only. Right. The answer is yes. They are a function of the input X, but that's a lot of things. So X is this entire sequence of length capital L, and with also a batch dimension, and D is like the sort of word embedding dimension here. And so to say that B and C, so A is not even a function of X at all in this framework, but B and C are. And so there's actually quite a lot of information in X here. And the S sub B here is what we took before to be just a simple, so it can be a little confusing here. So this algorithm is even more generalized than their model. So for them, S sub B is just a linear layer with n-dimensional output, but also, of course, this kind of B and L dimension coming along for the ride. S sub C is just another linear layer. S sub delta, which shows up here, is this linear sub 1, so project everything down to 1 dimension, and then broadcast it out to d dimensions, so kind of just like copy it. And then this like discretized step, so this is another kind of, another parameter for the model here. So there's different ways you can discretize things. They mention a few of them, and they come from numerical ordinary differential equation solvers. So one of them is called like zero order Auld. The very first one that you would learn in like a differential equations class would be forward Euler. There's also one called like the bilinear method, and they talk about different possible discretization methods, and like they seem to have settled on one that works best for them. Okay, let's see. I'm looking for questions here. Go back to this algorithm. Interesting, but in LSTM stuff, it also knows hidden state in here. They don't do ABC. That's right. Yeah, A is time invariant. So the time variance can be seen from this like parameter L here. So in B and C, we've got this like parameter L that's coming along, which means that the B at each time step, that, as we recall, like the B and C and A are all involved in the evolution of the H sub T. Those can change now. So that was the innovation from the S4 model, had the same B and C for every time step. And it turns out that was pretty limited. So that's the notion of like the selective state space model, that if the B and the C can change with each time step, then we can do more adaptive sort of evolution of this. And in fact, we can like change the B and C based on what has already happened, right? So what has occurred so far. Pause here for just a second. Questions. B and C only input of X, right? How does it change with time? Because X has the component of time. So X is the, one of the dimensions of X is this uppercase L. So you think of X as not just like one input, but the entire sequence of inputs. Okay. What's the main limitation versus the transformer? That's a good question. So one answer to that would be empirical. So if you look at the sort of empirical results, we can go there in a second, so in a transformer, you incorporate the word order, which you can think of as the time, right? So the dependency from one word to the next through this kind of like hacky add-on thing with all the sinusoids, right? Oh, any other links to your mind for a deeper dive? Absolutely, I'll give you some in a second. Because in the training mechanism, except for those like weird sinusoids that you add on, it does not consider word order. So everything is like completely parallelizable in the training. So if you can think of this as a limitation, they would present it as like, you know, their victory. They managed to take this inherently like time dependent model where there are data dependencies between doing inference or training at time t-1 and doing the same thing at t, and largely parallelize it, right? They couldn't do it completely because there are those dependencies, but we were talking about scans a moment ago, and so this involves like using some pretty great algorithms for doing parallel scans. So this is where you end up doing a little bit more computation than you absolutely need to in order to parallelize it. So certain things yeah, this is great. The annotated S4 is great. Okay, so the transformer is just so parallelizable in terms of its training, but it pays for that in that, when you do the next step of inference, you have to consider all of the previous words that you've already generated, right? So in order to select from the distribution, when you do this like autoregressive thing, you have to compute the k, q, and v for the previous words that you've already generated, like again, right? So it's not constant time inference. This is in principle constant time inference. So that's the advantage, but they've had to do a lot of work to make it more parallelizable in terms of the training. Okay, so I definitely recommend the annotated S4 in terms of a deeper dive. I think this conversation with Albert Gu is a good place to start in terms of getting intuition. I recommend Mamba Minimal as a place to start understanding the code. And then in terms of the math, I have to admit that it's these papers. There are about 6 of them, 7 actually, and it would be a lot nicer if they were published in like a book that would probably be about 65 pages, but instead it's about 7 papers that are each like 30 pages long, and they have appendices, and so it can take a little bit of time to amalgamate them into your brain. And then if you're not as concerned with the math, the idea is like, okay, so what are you going to make the parameters that you choose if you're going to sort of iterate on the model or make new versions of it? So definitely one thing is, let's go over for a second. So let's look at this. You know what? I think I'm just going to wrap up here. We're 2 minutes over. If anyone is interested in tracking a lot of the Mamba inspired work, yes, this is great. Yeah, Jason's page is really good. There's a lot of things going on. I imagine that there will be more very soon. Have you or anyone else here considered making your own blog post or page explaining these papers and consolidate it? I think that's a great idea. I think that whether it's one of us or somebody, like very soon there will be a more unified version of this, because people are very excited about this. Okay, I'll take a few more questions and then I will wrap up. So if you look at the annotated S4, you should be aware that that does not include Mamba. So the innovation of Mamba is to be not time invariant, right? So that's these kind of red things in the table here. It's time varying. And in order to accommodate that without doing like super expensive inference, they had to really get very slick with these like parallel scans. And that is the innovation of this thing called S5. So as far as I recall, S5, which is like the sort of next version of S4, as you might imagine, is not incorporated into the annotated S4. So if you read the annotated S4, which you should, and then you want to move on from there, you could look at the abstract of S5, which is this paper, which, by the way, is not written by Albert Gu or Tree Dao, or those folks. It seems to be kind of something coming in from the outside. And then look at the innovation of Mamba and maybe start with Mamba Minimal. And then if you want to get into some of their more advanced kernel fusion and stuff like that, you can look at the official repo for Mamba, which is very good too. I think the authors have done a really good job in terms of popularizing, I mean, not popularizing, but, communicating with clarity some of these. There's a lot of ideas here, and I think they come across very clearly compared to how they could have. Okay, so I'll pause for a few final questions here.
thanks for the presentation. One question, why wasn't this paper accepted to open review thing?
Oh yeah, that's a good question. I heard that myself. I don't, does anyone know any of the context there? I don't feel like I understand it.
Yeah, I just remember S/ being mad about it, but yeah, I'm not sure.
I
You said-
seem to recall that only one of the reviewers objected to this paper. Of the 5 reviews, 4 were very positive, and one was what sounded like a little bit snarky.
I see.